I've seen this next question several places online, and several people suggested it to me when I asked for interview questions. So this must be a really popular one to ask people, and indeed I think it exposes a lot of ideas in the Python programming world. So the idea is, well, let's start off with what's a Fibonacci sequence, right? It's a really cool mathematical sequence. Apparently it appears in nature in all sorts of places, but quite frankly, I mostly see it when software engineers want to torture other software engineers. And the idea is that you start off with 0 and 1, and then the successive number is the sum of the previous two numbers. So 0 and 1 is 1, and now 1 and 1 is 2, and 2 and 1 is 3, 2 and 3 are 5, 5 and 3 are 8, 5 and 8 are 13, 8 and 13 are going to be what, 21, 21 and 13 are going to be, now we're stretching my mathematical abilities, right? Then we're going to have, 55, and then we're going to get to 89, and so on and so forth. I'm going to stop there before I make a fool of myself. In any event, so that's the sort of start of the Fibonacci sequence. And the question is, right, write a function that will return, that returns the nth Fibonacci number. Right, so if just using these numbers here, this would be Fibonacci 0, 1, 2, 3, 4, 5. So if I were to say I should be able to say fib of 5, and it'll return 0, 1, 2, 3, 4, 5. It'll return, well, turns out that's 5, assuming I got that right. Okay, so how are we going to do this? Well, it actually turns out to be a little tricky in that you don't want to generate the entire Fibonacci sequence. I think that goes without saying. But if you've got a function that's going to generate the Fibonacci sequence, it's got to store its previous values somewhere. Right? It has to store the current two values so it can get the next value. And so a really traditional way to get the Fibonacci sequence is with a generator function. And generator function looks just like a regular function, except instead of using return, it uses yield. And yield says, I am now going to return this value to the iteration that I'm inside of. So that I should say also, generator functions expect to be inside of an iteration, like a for loop. And so it'll return that value, sort of go to sleep, and then wake up right after the yield. So I can say here def fib, or fib, and this is not going to be the final thing. And then I'm going to say here def fib, I'm going to say first equals 0, and second equals 1. And then I can say while true, and then I can say here yield first. And then I'm going to use tuple unpacking. I'm going to say first second equals second and first plus second. So what's going on here? Well, I have an infinite loop here, which might seem like a crazy thing to do because after all, infinite loop will run infinitely. As I like to say, it's good if you charge by the hour for your consulting work. So here, though, it's not exactly going to run infinitely because we have a yield, and yield says I want to return a value to the current iteration. And so long as we're not foolish enough to put our generator fib, whatever we get back from invoking it, inside of something infinite like list or tuple, we should be fine. So what's going to happen is we're going to, again and again and again, while true, we're going to yield first, whatever first is, it starts off at 0. And then we're going to do this unpacking. And the unpacking says, here I've got a tuple. I have two elements of the tuple from second and first plus second. Currently, that would be then, the first iteration, it's going to be 1, 1. And then we are going to assign them in parallel to first and second using unpacking. So first becomes 1 and second becomes 1. And then we go around for another round and yield is going to return 1. And then we're going to add to it again. Then yield's going to return 2, and on and on and on. The idea is, though, that I've got this generator function. So now I can say fib, g equals fib. And then I can say next on g. I can just invoke next and next and next. I can also say for I can do something like this. I can say for, let's do this. I'm just going to do g equals fib. I can just do this. For one number in fib, print one number, end equals, let's do a space here. And then I can say, if one number is greater than, let's say, 100,000, let's make it 1,000,000, then break. So I'm going to do this for loop here. I'm going to get more and more and more numbers. Looks like my numbers were actually pretty accurate. That's good. But you can see that they very quickly get very big. And so what's happening here is the for loop is turning to fib is turning to the result of invoking my generator function. And the result of invoking my generator function is a generator object. It's something that then knows how to fit within the iteration protocol. And we're going to say, okay, give me your next and your next and the next. Now, the fib generator is happy to give us an infinite number of numbers. But of course, we don't want that. So we're going to stop when we get here. So this hopefully is starting to give you a sense of how we can pull this off. So if I now want to say, I'm going to say def of fib n. So I want the nth Fibonacci number, and n is going to be here. So how can I do that? Well, what I can do is I can say, I can count the number of iterations I'm running on fib. So I can say here, for example, for, right, one number in fib, right? And then I can say something like this. I can say index equals 0. And I can say here, if index equals n, then I can just say return one number. So what's going on here? Oh, and then I have to, of course, say index plus equal 1. Otherwise, bad news. So what am I doing here? I'm basically saying my function here, fib n, is going to take n. It's going to start off with index. It's going to go around and around and around for one number in fib. But it's not going to print anything. It's not going to return anything until it gets to the number here that we've reached, index equals n. And when that happens to be true, we're going to return it. Let's see if we can do that. So if I say fib n of 5, it'll return 5. And fib n of 10, it'll return 55. And fib n of 100, it'll return that, which, as I'm sure you know off the top of your head, is the 100th Fibonacci number. Now, we can actually improve this function a bit more. Because the fact is, yeah, I'm keeping track of the index here, but I can actually use the built-in enumerate function. And that returns two elements. It returns actually a tuple of an index and the current value. So I can grab those through unpacking, and I don't need to worry about the maintenance of index, and now it just works, and I should get exactly the same numbers back, and indeed I do. So we actually solved this with two different parts. Let me copy them so you can see them together. The first part is going to be our Fibonacci, it's going to be I see, I copied the wrong thing. The first is going to be our Fibonacci generator, and that generates whatever Fibonacci number we want. And that's really important and useful, because it keeps it sort of isolated and insulated there by itself. The second part is going to be our actual regular function, which is going to invoke the Fibonacci generator, and then we're going to use enumerate to count through it and find the nth Fibonacci number as well. All right, you will never need to calculate Fibonacci numbers, I'm guessing, in your actual work, but on job interviews, they might well ask you about it.